The first situation we're going to look at is a donor impurity. And so this occurs when our dopant is coming from group 5 of our periodic table. So examples of this would be, like I mentioned in the previous video, phosphorus. So examples would be phosphorus, but we could also use other elements such as arsenic. And the key thing is that, of course, any element in that group is going to have 5 valence electrons as opposed to silicon's 4 valence electrons. So remember, as I said in the previous video, that our donor process is creating substitutional impurities. And so what that means is we can think of it as basically replacing a silicon atom in the lattice with, in this case, a phosphorus or an arsenic atom. So let's take a look at what that looks like in terms of our lattice here. So here we have a silicon lattice, and of course we can assume it extends in all directions. We're looking at sort of a small piece just for simplicity. But let's say we want to replace this silicon atom with a phosphorus atom, for instance. So we can come in here and we can get rid of our silicon. We also need to get rid of 4 of our valence electrons that belonged with that silicon. And now we're going to introduce a phosphorus atom. So our phosphorus has 5 valence electrons, so 4 of those can bond with the 4 neighboring silicon atoms, and then we're going to have a 5th electron, which is more loosely bound than those other 4 that are bonded. And so of course what that means is that that extra electron that's represented by the dot here can pretty easily break away and become a free electron that's moving through our silicon lattice. When that happens, we notice that this P, which is left behind, is going to have a net positive charge because we've stripped one of our electrons away from our phosphorus. So let's sort of formalize a couple of these observations. So our 5th valence electron from our phosphorus is donated to the silicon lattice. And so this is why we call them donor impurities, is because they are donating electrons to the lattice. So donated to our silicon lattice, and once it's donated, as I said up here in the diagram, it's now free to move about the lattice in our conduction band. So another important thing to notice is that this ionized phosphorus is fixed in the lattice and cannot move the same way a hole can move. So our ionized P+ atom is fixed and cannot move. And so ultimately what that means is that we have created a free electron, or we could also call that a conduction electron, without an associated hole. And so this is again something that I alluded to in the previous video. So without associated hole. And so we'll see why that's important in terms of creating certain devices a little later on. But another important thing to keep in mind too, I should say, is that this ionized P+ atom is fixed, so it can't move. So we'll come back to that when we're describing our p-n junction diode a little later. The one other thing to note too is that if we're talking about donor impurities, of course we see that we're going to have more electrons. And so I should mention too, of course, we're not just replacing one phosphorus, we're going to be replacing several phosphoruses or several silicons with phosphorus throughout our lattice. So when we have these donor impurities, what we're going to see is that we're going to have more electrons. And so just some terminology is we can say in this case our electrons are something called the majority carrier. So we have majority carrier electrons. And so the reason we have to specify that these are majority carriers is because our holes are still going to be present. So for instance, looking at this lattice, maybe an electron over here has enough thermal energy to break away from our lattice. So maybe this electron is going to break away and it becomes a free electron in our conduction band over here. And of course, that's going to leave behind a positively charged region, which we're calling our hole. So we are still going to have holes. We're still going to have free electrons due to electron-hole pair creation, but if we dope it correctly, the electrons from our phosphorus are going to dominate. So coming back to this terminology down here, if we have these donor impurities, we say our electrons are our majority carriers. And again, that's just simply because we have more electrons than holes. And remember, of course, our electrons are negatively charged. And so because our electrons are negatively charged with an N, we say that this is an N-type semiconductor. So sort of just one thing to remember is if we have donor impurities, then that corresponds to N-type semiconductor. And as you might guess, we're going to look at another type of semiconductor when we have another type of impurity. One quick thing I want to note before I forget is you might be asking yourself, how do we actually get this phosphorus atom in our silicon lattice? And of course, that's a whole nother course we could spend talking about that topic and similar processing topics. But just to give you a couple sort of key words, if you're curious about looking further into that, there's a process called diffusion, or more commonly today what's used is something called ion implantation. And so both of these are processes by which we can introduce impurity atoms into our silicon lattice.